Hello, and welcome again to Chemistry with Mr. Olson. Today we're going to solve some problems on the Le Châtelier's principle worksheet. Le Châtelier's principle is about equilibrium reactions, where the reaction arrow goes both ways, the forward reaction and the reverse reaction. So if you'll notice on the worksheet, all the arrows are double pointed. They go both ways. And you'll also notice where a delta H value is given, I have already added in the absolute value of delta H onto the proper side of the reaction. So if it's exothermic, if energy is released, heat is a product. And we add in the 92.2 kilojoules on the right here for reaction 3A. But if it's endothermic and energy is absorbed, then the energy is on the reactant side. That makes it easier to solve the problems. Question 3 is actually a great stepping stone to discuss what an equilibrium can do. And I don't know if I said, Le Châtelier's principle is equilibria resist change. Equilibria resist change. So if you make any change to a system at equilibrium, which is in balance, then immediately the system will respond by opposing that change. And in fact, the diagram we have in our today's notes, it shows here's a system at equilibrium. The concentrations of the reactants and products of this reaction, called the Haber reaction, they're constant until at a certain time, we make a change. We add H2, and as a consequence of that addition, immediately the equilibrium shifts. You can see it responds by our adding of H2. It responds by immediately using up some of that H2, removing some H2, reacting some H2. How does it do that? How do you get rid of H2? How does the equilibrium do it? It shifts to the right, and it uses up the reactants, including the H2, and makes more products. So that's an example of Le Châtelier's principle, where we make a change, we added H2, and the equilibrium resists the change, and it does this by shifting to the right. All the equilibrium can do is favor one reaction or the other, but that's how it does it. So let's work out some examples. All right. So in 3A, the question is, what happens if we increase temperature? If we increase temperature, then the equilibrium will shift to get rid of that added temperature, so that added heat energy. So in this case, it will shift left. For 3B, if we increase temperature here, we add in energy. How does it shift to get rid of the energy? Well, it shifts right to use the reactants, including the energy, and make the product. So there is that one. And in fact, it works the same way for all three endothermic reactions. If we increase temperature, add more heat energy in, then it will shift right to absorb some of that. It opposes the change. Okay. Now, let's do the second part of that. In our notes, we talked about the rules for pressure. And Le Châtelier's principle works the same for pressure. If you add more pressure, the equilibrium shifts to remove pressure. Now, pressure depends upon the number of gas molecules. So what we're going to do is compare the number of gas molecules on each side. So let me do 3A here. We have 4 gas molecules on the reactant side. 1 plus 3 equals 4. 2 on the right. So if we go from 4 to 2, that's less pressure. If we go from 2 to 4, the reverse reaction means more pressure. The question asks, what happens if you increase the pressure? If you increase the pressure, the stubborn child equilibrium will resist the change and do something to reduce the pressure, and it does that by shifting to the right from 4 gas molecules to 2 gas molecules. So it's a shift to the right for that one. The next couple are interesting in this regard. Remember, it's the number of gas molecules. Liquid molecules don't count. Liquids are basically incompressible. So we have 0 gas molecules on the left, 1 on the right. So if we increase pressure, it will shift towards fewer gas molecules, and in fact, that's a shift to the left. Number 3, C is tricky because we have 2 gas molecules on the left, 2 gas molecules on the right. We have the same number. So the effect there is no change. No change. All right, let's answer one more problem. Let's answer number 2. Here we have the reaction written with the energy included in the equation, which I really like. And the question here doesn't ask which way it shifts. It says what will happen to the concentration of NO, nitrogen monoxide, the product, at equilibrium if we add more oxygen. So if we add oxygen, the equilibrium will resist that change and do something, shift, to get rid of some oxygen. Well, it shifts to get rid of oxygen by shifting right, which is the forward reaction, using up oxygen to make NO. So if we shift right, the concentration of NO increases. So the answer is, if more O2 is added, we have an increased concentration of NO. NO shifts upwards. What if we remove N2? If we remove N2, then the stubborn child equilibrium will do something to add N2. What can it do? Well, if it shifts left, if it does the reverse reaction, it's going to take some NO and it's going to make some O2 and some N2. And that means shifting left means the concentration of NO is going down. So if we remove N2, it will shift left and we will have a decreased concentration of NO. What if we increase the pressure? Well, let's count the gas molecules on each side. 1, 2 gas molecules on the reactants, 2 gas molecules on the products. No, it's 2 and 2, so pressure has no effect. So no change. No change in the NO concentration. What if we increase temperature? If we increase temperature, the stubborn child equilibrium will do something to get rid of that added heat. And how it gets rid of heat is shifting to the right, gobbling up the temperature, the heat energy, and reactants to make the products. So if it shifts right, the concentration of NO goes up, and we have an increased concentration of NO. So that is Le Châtelier's principle. Remember, write your delta H values into the equation. It makes it much easier to figure out the effects of Le Châtelier's principle. You can just see if the heat energy is a reactant or a product. And remember, gases, pressure has to do with the number of gas molecules on each side. The number, liquids and solids don't count. So I hope this has been helpful, and I wish you a wonderful evening. Ta-ta.